Welcome back, and this video will look at some properties of the region of convergence for Z transform, and they will be quite similar to those that we defined for the Laplace transform. So the first property of the region of convergence for Z transform is that ROC of some transform, say x of z, of some transform function, it will actually consist of a ring in the z plane. Fine. So it will be in terms of rings centered about the origin. Fine. Because these are polar coordinates, we know that the factor z, it is actually equal to r e raised power j omega, and in terms of polar coordinates this actually represents a circle of radius r. So accordingly your ROC, it will be a ring, it will be a circle in the z plane. Now what will be the exact nature of this ring, of this circle? It will depend from case to case, but in any case, in generally speaking, it will be a ring in the z plane. Fine. So if you remember, for Laplace transform, it was a portion, it was a, you can say, another region, yeah, strip in the s plane. Fine. So that plane now gets converted into a ring. Second, by definition, region of convergence is the area where your this system function transform, generally speaking, your transform will converge. That is, it will have a finite value, which by default means that ROC, it will not contain any poles, because a pole is a root, or it is a point where your transform, assuming it to be a rational function, having a numerator and denominator polynomial, it makes your transform infinite. So ROC will never include a pole. Then we had that if x of n is a right-sided sequence, then its ROC will be exterior of a circle. Fine. That means in this case, if it is a right-sided sequence, here is my real axis, imaginary axis, and you have some point, say r naught, and we draw a circle around this, and ROC will be this, the exterior of this circle. Fine. So it effectively means, we slightly put it in a different way, that if the circle which is drawn at the point z is equal to r naught is in the ROC, then all finite values of z for which magnitude of z greater than r naught, they will also be in the region of convergence. Simpler terms में, if you have a right-sided sequence and if z is equal to r naught is a part of your region of convergence, then all the other points which lie external to that circle defined by r naught, they will be the part of the ROC. Just simply put, it will be an exterior of a circle. Then contrasted this, if your x of n, if your signal is a left-sided sequence, then the reverse will happen. So ROC will be interior of a circle. Okay, so in that case, it will be like this. Again, it means that if you have a point z is equal to r naught, and that point is a part of ROC, then all the values from 0 to that point, they will also be a part of the ROC. Simply put, you have a what you call a left-sided sequence. It will have a region of convergence that will be actually defined by the location of poles. And since ROC cannot include a pole, so obviously it means you will have a pole on the boundary, and a circle through that pole, and the interior of that circle will be actually the region of convergence. Right? If you compare this with the Laplace transform, we had similar kind of definitions, that if x of n was right-sided, then the region of convergence will be towards the right of the rightmost pole. Right? Similarly, if it was left-sided, it will be left. Right? And then fifth point, that if x of n is a two-sided sequence, means it extends to infinity from both sides, from minus infinity to plus infinity, then ROC will be a ring, an annular ring. That means it will be something like this. Between two circles, the portion, this will form the region of convergence. Fine. Then there is another point, that if x of n is now a finite sequence, means it is well defined between two finite points, say between n1 and n2, because earlier three cases, right-sided sequence, it extended from 0 to infinity, so it was an infinite sequence. Left-sided sequence from minus infinity to 0, again an infinite sequence. Two-sided sequence from minus infinity to plus infinity, again an infinite sequence. Now in case you have a finite sequence that is well defined between two finite points, say n1 and n2, then ROC will be, in such case, then the region of convergence, it will be the entire z plane except possibly at z is equivalent to 0 and or z is equal to infinity, which would actually depend upon the nature of the sequence, right? But generally it will the entire z plane. Then depending upon the specific nature of the sequence, it may or may not include these 2 points. Again, these are quite similar to the properties that we did for the Laplace transform. Right? Then finally, we are interested in how to express causality and stability in the Z transform. Fine. So you know that for an LTI system, which is discrete in time, the response y of n is actually given as a convolution of the input x of n and the impulse response h of n. Now if I take the Z transform, just like a Laplace transform, this gets transformed into multiplication. That is this. Convolution gets transformed to multiplication. Fine. And h of z in general is known as the system function. Sometimes some literature it's referred to as transfer function, just like the Laplace transform. And if we evaluate this h of z at z is equal to e raised power j omega, along the unit circle, then this simply becomes the frequency response of the system. Right? Now, as far as causality is concerned, we have the causality of an LTI system in terms of its impulse response. It is defined that impulse response is 0 for n less than 0, which means for a causal LTI system, your impulse response is actually a right-sided sequence. which means that the region of convergence ROC of h of z, it will be the exterior of the circle in the z plane, right? And it will include z is equivalent to, because it is the exterior of the circle, it will cover the entire z plane, bearing that the interior portion of that circle, because it is a right-sided sequence, right? And this in turn becomes the condition for causality in terms of the z transform. That is, we define a discrete time LTI system is causal if and only if the exterior of the circle, yeah, if it is ROC is the exterior of the circle in the z plane, and it will include a point z is equivalent to infinity, right? Again, it quite resembles with the definition we had for the Laplace transform, right? Just that वहाँ पे आपका strip था, plane था, यहाँ पे it is a circular portion. Now, as far as stability is concerned, stability में we had that impulse response should be absolutely summable. Okay? Which means summation n runs from minus infinity to plus infinity. H of n, it should be a finite value. Fine. Now, if this is a finite value, it means Fourier transform of Hn exists. Fine. And we just established relationship between the Z transform and the discrete time Fourier transform, wherein we concluded that discrete time Fourier transform is Z transform evaluated over the unit circle. Right? So if you combine these three equations, yeah, these three logical definitions, we can conclude that in terms of Z transform, so it is something like this: a discrete time LTI system is stable if and only if the region of convergence of its, not impulse response, it will be system function a transfer function includes unit circle. Fine, it is based on this, because Hn has to be absolutely summable, which means summation n runs from minus infinity to plus infinity. H of n, it will be finite, it will be less than infinity, which means its Fourier transform will exist, and Fourier transform is the Z transform evaluated around a unit circle, which means an LTI system is stable if and only if the ROC of its system function includes the unit circle. So this is the condition of stability and causality in terms of the region of convergence as defined in Z transform. So if we have some typical cases, for example, if the region of convergence of system of function is, let's suppose something like this is point 2, through this we'll draw a circle, and let's suppose region of convergence is the exterior of that circle. Including the point infinity somewhere here, right? So this will typically be a causal system. Causal in the sense because the region of convergence is the exterior of a circle and includes point infinity. But this cannot be a stable system because one will be somewhere here, and the region of convergence, it does not include the unity circle. So this is the ROC for a causal system but not a stable system. Okay? Similarly, if we have something like this, and let's first draw the unit circle, and we have a region of convergence, say this is some finite point A, and region of convergence is the interior of this circle. the exterior circle, the outer circle. Now this is not causal because it is not exterior to this circle and it does not include the point infinity, but this is stable because it includes the unity circle. So this is the ROC for the stable system. Similarly, we can have different cases. For example, if one of the cases is like this, say this is unit circle and we have an ROC exterior to the inner circle like this. Fine. So in this case it is the exterior of the circle, so it is causal, and it also includes the unity circle, so this is stable as well. Okay? So we can have different permutations, and by looking at the ROC you can actually tell whether the system, yeah, to which, yeah, this system function, it will be corresponding to some system, whether that will be causal, stable, or whatever the case is, but for a discrete time system, right? So this is all about Z transform. Like I said, you will be studying in detail in your digital signal processing course somewhere in 7th semester. Usme some other aspects, some other properties of Z transform which we have not discussed here, you will take them in detail because of the shortage in time, I just thought at least you should have some idea of Z transform, right? And you'll see that it has a significant amount of resemblance with the Laplace transform. The way we define the Laplace transform, and then its relation with the Fourier transform, then its properties, and the way we express stability and causality in terms of the ROC, you will see that there is a great deal of similarity, right? The only difference being in your Laplace transform we have the S-plane, which means the region of convergence is basically a strip, it's a plane region, whereas in the Z transform it is basically in the form of a ring, and depending upon your time domain sequence the ring can take different forms, fine. So that's all about Z transform. Thanks.